All right, so let's start with 2005. Let's be crazy and go in order. Okay, hopefully I have the entire test in front of you. Randy, did you get one?
Wait, there's one right here.
Okay, cool. All right, so let's be nuts and go in order. So now what you should know is that this test goes in order of atomic structure through nuclear chemistry. The crash courses that I have cover those in order. So you should know where you are in the test. Sometimes that can help you figure out a problem. So starting 1 through 30, the entire test goes from atomic structure to nuclear chem, pretty much in order. And then from 31 to 50, it does it again, but a little differently. So number 1, you're in atomic structure area. You can expect things about the models. You can expect things about protons, neutrons, and electrons, and all that fun stuff in between. But here we are at number 1. Let's be up close and personal with it. Okay? And here we go. Rock on. In a modern wave mechanical model of the atom, orbitals or regions. Now stop for a second. A modern wave mechanical model. Now, there's a bunch of models that are responsible. This one tends to get the least amount of play. What makes it the modern model? It's our current model. What makes it a wave mechanical model? It's the model that electrons are acting as waves and as particles. Sometimes you hear the word wave-particle duality. Now, what makes it a wave model is that we don't know exactly where a wave is. We say electrons are in a region, and you should understand where the word comes from. So sometimes they call it the electron dot diagram. So you have your positive nucleus, and then you've got your electrons that exist in a certain region. That region is based on probability. We can say with a certain probability electrons are in this region. For those that learned it, this would be the shape of an s orbital. Okay, now you don't have to know s orbitals for this test, but we would say probability is something you'll hear. Okay, so probability you'll hear. This region of space where electrons exist are not orbits. They're in a region called orbitals, and that's a big difference. And I'll say this again, the Bohr model, which is not part of this question, but it's built into it. You should know that the Bohr model was a model where you had a positive nucleus and you had electrons traveling in circular orbits, a planetary model. Now, what Bohr did was so important because he said that electrons travel in these circular orbits based on distinct energy levels called quanta. To get to one to another, you need an exact amount of energy. And when they jump away, you should know that they absorb energy because to exist farther away from a positive nucleus, you need more energy. And when they jump back, they give up the energy in the form of light. He explained hydrogen. All that great work was really, really groundbreaking to say that the atom is quantized, has definite energy levels. But it wasn't correct. It was only good for hydrogen. So to give Bohr credit, they used the word orbit and added AL saying orbitals. It's a region of space based on probability. So when you hear the wave mechanical model, electrons act as waves. Electrons exist in regions of space based on probability. And 3, they exist in these regions, not of orbits, but orbitals. So obviously the answer, of course, is number 3. But I'm giving you all the background to that question. Okay, because you may see a question similar based on the same topic or concept, but not exactly the same question. So we're back with number 1. And please stop me, wave me down. Okay, give me the hitchhike signal. Say, Mr. Grodski, I don't get it. Do that again. Or could you do? I'll do anything here except probably round-offs and out of space. Number 2, compared to a proton, an electron has... Okay, well, comparing a proton to an electron. Some people say, man, this is the stuff I have to memorize, just like possibly global or something. All right? And I say, you don't. And many teachers don't utilize this reference table. Okay, and I'm going to go to it now, I think. And this is reference table O. Okay, not this. And maybe I'll find that. Maybe it's there. I think I have to pull it up, sorry. So my reference table O, let's pull it up. SkyDrive. Let's go honors chemistry. Let's go, not there, to my reference tables. And it was open. So let's go to table O. And people pull this up for nuclear chemistry, but many people underutilize this table for regular old atomic structure. Not everybody. So here's how I'm going to use this. Okay, now the top number is my mass number, bottom number is my charge number. Now a beta particle, although I don't mention it anymore, is an electron. Okay, yes, it's an electron that comes out of the nucleus in nuclear chemistry, but this is an electron. Okay, our neutron has a mass of 1. Our proton has a mass of 1. The bottom numbers are charge. So a proton has a charge of +1. a neutron a charge of 0, it's neutral, and the charge of your electron is -1. So look at the differences. You can do this here. So I forgot the question. The question was, how does a proton electron differ? Protons, okay, have a mass of 1. Electrons are considered to be so tiny there is no mass, except they really are 2,000 times lighter. That's something that does pop up once in a while. But they have what? Opposite and equal charge. One is +1, one is -1. Okay, so something you could use in terms of trying to figure this out. So, back to where I was. So compared to a proton, electron has the same quantity of charge. One is +1, one is -1. And of course, opposite sign. I know many of you would know that without having to look at the table O, but it's nice to go if you get crazy and get caught up. It's there for your viewing pleasures. So number 2 is pho, or as we say in North Riverhead, pho. Okay? Number 3, which two notation represent atoms that are isotopes of the same element? Iso means same. Okay? So you should know that if you're the same atom, you have the same number of protons. It's the social security number. Atoms differ not by not by electrons, not by neutrons, but by proton number. So clearly 3 and 4 are gone. In fact, a notation that people get messed up all the time is notation I want to show you. So 3 and 4 I'm going to just throw out because they make no sense. They're different atoms. Isotopes are the same atom, heavier and lighter form, sometimes radioactive form. Now I could write this differently. I could just take this away. Take this stuff at the top away, say bye-bye. Okay, let's say I take tin 121 and tin, okay, 119. And people get messed up with this notation all the time. They think that that is some number that I should know and I forget what it is. It's the mass number. If it's tin, 50 is implied. Only tin can be 50 protons, so they're telling you exactly the mass number. Why? Because when you say you have tin, that's too vague. Tin what? What form of tin do you have? Now, most of you guys don't talk like that on the weekends, but when I do, I say, well, I have tin 121. You know? I have tin 119. Well, so what? I got a tin 121. Which tin do you have? Because every single element has a form of some different number of neutrons. So obviously, this is denoting the mass number. Okay, so obviously, this is not an isotope. This is the same atom, same number of neutrons. To get neutrons, we subtract this mass number from the proton number. Why? The mass number for the neutrons and the protons are the same. This is protons and neutrons. This is protons. So subtract, you get protons. Okay, so clearly 3 is 1. Okay, and you know some famous ones that we've been dealing with throughout the year, I'm sure. Carbon dating, right? Carbon 14 and carbon 12. What's implied?
Atomic numbers.
Yeah, 6 is implied. We don't write it because we're cool like that. Okay? But this is carbon with 14 minus 6, 8 neutrons. This is carbon with 12 minus 6, 6 neutrons. Just a lighter, heavier form. Okay, isotope. Big, big, big concept that's going to come up somewhere, somehow in your test. Okay, number 4. Elements on period 5, that's going to be the row 5 on the periodic table, are arranged left to right in order of. Well, this is a fancy way of saying how are the atoms arranged. Okay? Now, this is a tricky question sometimes because, let's see, where is my reference table thing behind it? Okay? This is sometimes a tricky question because some people think they're in order of atomic mass. Now, they said period 5. That's the 5th row. Now, it could be any period they picked. And you may say, wow, atomic mass number is increasing. Okay? And I wouldn't go for that because I know the periodic table originally was put together based on atomic mass only because that's the only thing they knew about atoms way back when Dmitri Mendeleev was putting the table together. But we rearranged the table so that we increase with the proton number. In fact, I bet if we go through the period 5, and I don't know about period 5 as well as period 4 and 3, that there might be an instance where it doesn't go in order. Although I'm hard-pressed to find it. Yeah, this is a lousy question. I mean, you might, oh, there it is. Okay, so there's an example where the mass doesn't go in order. Okay, in fact, when they had Dmitri Mendeleev's table, these guys were actually switched. And they switched them back when they discovered in the 30s the proton number, and they put them in order. The periodic table is arranged by the atomic number, the proton number. Don't fall for the mass number. Okay? So back to reality. Up there goes gravity. And there we go in order of increasing atomic number, choice 4. Number 4 is 4. Okay? And again, we're into periodic table. We went to atomic structure. Now we're in periodic table questions. You can see how this is going. And now another periodic table question. Which list of elements contains a metal, a metalloid, and a nonmetal? Okay, so let's go back to the periodic table. And we should know what are our different forms or different types of elements from this table. Okay, first and foremost, party people. What breaks the line between are your metalloids. So here are your metalloids. Your barium, your silicon, your arsenic, your tellurium, your germanium, and your antimony. These break apart your nonmetals to your metals. Now, what defines a nonmetal? Generally speaking, my friends in chemistry, small radii. As you go across, they get smaller. As they get smaller, they attract electrons more. They love to get reduced. They love to gain electrons. Why? They have a lot of protons for their same energy shell. Metals are bigger. Their electrons are farther away. Don't make me get the doll out and swing it around. These guys tend to lose electrons. Why? Because electrons are physically farther apart. Their nucleus doesn't have the same strength. The electrons can migrate farther. Now there's a reasoning when you go down the periodic table, the nucleus or the atomic radii gets bigger. What is that? What's the reasoning why it gets bigger as you go down? It's called the, yeah.
The first ionization energy decreases.
It does, but why? It's all based on radius, and the reason is that what? That kindergarten effect. I was out in Tanger, I was shopping at kindergarten, I took my wallet. I left. So I went to get my wallet back. 40 of his kindergartner friends jumped me. And they held me down. I don't know how many kindergartners you could take, but I couldn't take 40. So they held me down, tickled me, and I couldn't get to the kindergarten with my wallet, so he won. He was able to run farther away from me because the other kindergartners were shielding me. So as you fill energy levels or shells of electrons or orbitals of electrons, if you go with the modern model, okay, it's harder for the positive nucleus to feel the negatives on the outside. So they're able to go farther. Now as you go across, the opposite is happening. You're not filling shells of electrons, you're adding protons to the same shell. So the nucleus has a greater effect on pulling them. So all up and to the right are your nonmetals, are the smallest atoms. They love to gain electrons. Over and down are your big atoms, love to lose. And essentially, big atoms, metals. Small atoms, nonmetals. Small atoms gain electrons, have high electronegativity, hold on electrons so tight it takes so much energy to pull them away. We call it ionization energy. Their attraction for electrons pulls electrons in closer. It's called electronegativity. But back to this question. Small atoms, nonmetals. Big atoms, metals. So metalloids have properties of both. Okay, so they want to know who is in between, who is small and who is big of that group. Okay, let's go back to the question. Okay, so which less is a metal, metalloid, and a nonmetal? Okay, well, I want to be careful. They want it in this order. So metal. I'm going to get rid of choice 4, because that's fluorine, chlorine, bromide, okay, or halogens, which are the most reactive nonmetals. They're above the staircase. Okay, I'm going to get rid of choice 2, because silicon is a metalloid. It's on that staircase. They want a metal first. All right, so 3 is going to be my answer because I have cadmium, okay, metal below the staircase, okay, antimony, all right, is part of that group that I just outlined as your metalloids, these two, and this line here, and then I have iodine on the other side. So those are the 3 that go in order. And you shouldn't get those wrong. Okay, any questions, please stop me, wave me down. All right, yes?
Polonium is just considered a metal then?
Yeah, polonium, anything below these guys right here are usually radioactive elements. Okay? And tellurium, that's good enough. So number 6, all right, number 6. Examine a physical property of an element, its ability to, well, first of all, reacting with an acid or reacting with oxygen implies breaking bonds and forming new bonds. Anytime you have a chemical property, you're going to make something new. You're going to pull bonds apart and re-put them together and create some new compound. So this is a chemical property. Physical property is where you test something, but you're not changing or affecting its composition. So noticing its color, figuring out its density, noticing its melting point, all those are physical changes. So form a compound, it's forming something new. So 1, 2, and 3 are all chemical properties. Now, dissolving, you should know a solution, my friends, is a mixture. It's a homogeneous mixture. And when you make a mixture, you're not creating bonds. Here's my mixture. I just made it physically, and I can separate it physically, because there's no chemical bonds. So that's why when you make a solution, which you should know is a homogeneous mixture, making it's a physical process. And separating the water from the solution is a physical process. What's an example of separating a solution from water from the solute in a solution?
Filtration.
What's that?
Filtration.
No.
Evaporation.
If there was some solids undissolved, you'd be right. You cannot filter something that's dissolved. So if you take if you took salt water from the beach, Rogers, and you put it through a filter paper, you don't get salt.
Yeah.
But people pick that all the time in part 2. So understand, even though even though this question is number 6 in the multiple choice, its implications are in part 2. That's what I'm trying to give you, every roundabout way. So not filtration, something else. Evaporation, boiling. Remember distillation? Distillation is when you separate things based on their different boiling points. Well, the water has its own boiling point because it's still part of a mixture. In a mixture, the components retain their individual properties. Like you take fuel oil, kerosene, gasoline. It comes in a big barrel called crude oil. What we do is we heat it, and we basically separate it based on its different boiling points because it's a mixture. Okay? So number 4 is the answer. Okay? Again, as you see what I'm doing here, yeah, we're going over the questions, but I'm going over the concepts. Number 7. All right? You can separate something based on chromatography, too. Okay, chromatography, another physical separation. Okay, number 7. Which element is malleable and conducts electricity? Okay, we're still in the periodic table stuff. Now, malleable means, okay, you can heat that sucker, and you can shape it into any shape. You can't do that with the stuff you use to make your dinner plates, can you? Can you make a wire out of ceramics? No, it's going to break. They're brittle. Things that are brittle are nonmetals. And here's the reasoning. Nonmetals are big or small. So they hold on to their electrons tightly. So if me and you were in a chemical bond, covalent bond, we're both highly attracted for electrons, okay, me and you. We're going to hold them tightly, right? So if you apply me a stress, we're going to break. And that's what plates and ceramics, anything made of nonmetals tend to be brittle solids. Metals aren't worried about electrons right there. They're kind of like free spirits. They're electrons. Hey, I'm a nucleus. Well, what's up, man? Yeah, where's my electrons? My electrons are all over, man. Like, where's your valence? My valence are at your house. Your valence are at my house, man. And, yeah, I'm attracting yours. You're attracting mine. You twist me. I don't break because I'm cool like that. I'm set, you know. These guys they're not OCD. Non-metals and non-metals are OCD. These are my electrons. These are yours. Okay, I want them, you want them, we're forced to share. Metals are like, what's up? Yeah, my electron's over there, mine here. We're all attracting together. And you can't ruin this guy's day. You know what we're talking about. Okay? He's so far from OCD. So metals have a lot of electrons. They're not held tightly. They undergo metallic bonding by attracting simultaneously everyone's electrons. Hey, we're all connected, peace and love, right? So you twist this guy, he's not going to break. So you can shape a metal because of its metallic bonding. And the reason why it conducts electricity is because its electrons are held loosely. Think with me. How does charge conduct it? If I put a negative here, if my electrons are free to move, they're repelled by negatives. And these electrons that moved, guess what? Repel the what? Other ones. And charge gets conducted. But if I'm in a non-metal scenario and I'm holding electrons tightly, my electrons aren't free to move. So they can't conduct. So they're screaming to you, this is a what? Property of metals. If you don't like this, which one's a metal, which one's a non-metal? Iron. To the left of the staircase. Sulfur. Above the staircase. Okay? Phosphorus. Above the staircase. Iodine. The only one that's a big atom is your iron. Ductility is another one they could have mentioned. What's ductility? The ability to draw into a wire. Of course, it would have to be metals. Okay, number 8. At STP, solid carbon can exist as graphite or diamond. These two forms of carbon have what? Well, they have the same properties, same crystal structures. Let me help you. Structure is king in chemistry. You'll learn this more about in organic chemistry, but structure is king. What I mean by that is you change the structure, you change the properties. Taught my kids that rubbing alcohol, okay, isopropyl alcohol, and regular propanol have the same exact chemical formula, but because of the different structure, one is deadly and one isn't. Okay? Carbon and graphite, graphite and diamond are made up of pure carbon. One is pure carbon, the other one's pure carbon. But my friends in chemistry, they have different structures. Diamond, you're not going to write on a pencil with. And you're not going to wear a pencil tip as a ring. Maybe you could sharpen it once in a while, that'd be kind of cool. Maybe you could write with it, but these are both made of pure carbon. What's different about them? Their structure. Graphite, look at the structure of graphite. Graphite, of course, is what's in pens, or pencils, I should say. They always said lead was, but no, it's really graphite. And think with me for a second. Doesn't it make sense that this will slough off? And that's why pencils can write onto paper. Diamonds are not going to do that because of their different structure. So different structure, different chemical, different physical properties. So, different properties, different crystal structures. That's something that you guys should know from organic chemistry. Okay, structure is king. Number 9. What's the form of titanium oxide? Now, two things scream at me with this one. I see oxide. That was oxalate, sulfate, sulfite. I would go to table, what the heck is that, table E? But by seeing an IDE ending, it reminds me that, hey, this is just going to be titanium and oxygen. This is a binary compound ending in I. Now, of course, the choices are all binary. Now, why do I have Roman numeral 2 there? Well, because party people, the people that want to go to the party, okay, let's just make this clear, because I can, and I'm tall. And, well, why is it titanium 2? Well, the reasoning is titanium has multiple forms. Okay, let me show you that. Reference table, let's see here. Cancel that. Maybe we go here, reference table. So, titanium, Ti. Okay, titanium can be +2, +3, or +4. So when you say titanium oxide, there's three different ways to write that. Now, when you said sodium chloride or sodium oxide, these guys only have one oxidation state. There's only one way to write it, so you don't need a number. But when you deal with your transitionals or elements that have multiple oxidation states, you need to tell the person which form, because as you just learned, different number of atoms will give you a different structure, different properties. So if you're looking for a certain type of titanium oxide, you need to be more specific. So titanium 2 means we're dealing with the +2 charge. Okay? So you go back to the problem. And so I'm dealing with titanium, Christmas in July, titanium, that's +2. It's not the second choice, it's the actual charge of titanium. Oxygen, if you didn't already know, is O-2. Now, if you didn't know that, okay, you go back to the reference table or the reference table. Let's slide on over to the non-metals, doing the non-metal slide. Here we go. All right, now we got oxygen. Okay, maybe. All right, let's get rid of that. So we've got our oxygen up close and personal here, and it's -2. Now there's other charges for oxygen, they don't have to tell you, but just pick this one for most of the time. So oxygen's -2. Titanium, of course, is +2, and you put it together. Now, obviously it's TiO, and Bingo was his name, okay? But Some people like to crisscross, that when you make a compound or a chemical formula, it has to be electrically neutral. So I need one of these to one of these. Now, if you like the crisscross method, this 2 goes down here, this 2 goes down here, make sure you reduce to lowest terms, because this is an ionic compound. Metal and nonmetal does not make a molecule, it makes a crystal. Crystals are patterns, repeating patterns of positive and negative ions. So this crystal pattern could look something like this, and it keeps going. What's the chemical formula of a pattern? Well, you would give me the what? The smallest pattern. Ionic compounds are always empirical because they make big crystals. And to give me chemical formula of a crystal, you would never count the ions in the crystal you actually have. You would just give me the lowest ratio of the ions in the crystal. So ionic compounds are always empirical. Molecular formulas are molecules. They have an exact number. Okay? So 9 is 1. Moving forward. Let's bring back the question. Okay, number 10. Ordas sane. 10. Which substance can be decomposed by a chemical change? Well, we've kind of talked about this already. Physical change is the change where density, melting points, you're not changing the chemical formula. This one, I have to break bonds or form new ones. If you look at this question, calcium, potassium, copper, those are elements. Those don't have any bonds. Okay, and how do I know? They're listed somewhere. So calcium, potassium, okay, and copper, these are all elements. And if you don't know this, table S is your friend here. Going to table S, making this smaller, coming down. Table S lists what, party people? It lists the symbol and the name. Some people say, how do I know the symbol name? It's listed in table S, the most underutilized table. Okay? And what was the point of the question? I lost my train of thought. Oh, right. So they gave you what? Elements. So you can actually find the elements here, and you know that they can't be broken down. Mr. Grodski, how do I know what ammonia is? Well, believe it or not, and that's why I'm here, there's another place you can look for ammonia. Ammonia is considered to be a base. So if we go to these tables here, you'll see ammonia is listed. Now you should know ammonia is NH3. You really should, from the experience in lab or in this course. But it's given to you. This has 2 different capital letters, 2 different elements, which means that this could be broken down into individual atoms, whereas the other ones were already just atoms. So that's why that answer, that's why that choice is ammonia. It's the only one there that's a compound. It's the only one there where you're breaking 2 different capital letters. Choice 4. Number 11. A chlorine atom becomes a negative ion. The atom